What if I told you that the emptiest space in the universe isn't empty at all? That what we call nothingness is actually a seething, bubbling ocean of energy, a hidden world where particles flicker in and out of existence in the blink of an eye. This is the quantum vacuum, the very fabric of reality itself, and it's anything but empty. Think of it as the stage upon which the entire cosmic drama unfolds, a stage that's alive with mysterious forces we're only just beginning to understand. Scientists once believed the vacuum of space was just nothing, a void, but the deeper we looked, the stranger it became. The quantum vacuum is a realm of paradoxes where energy arises from nowhere, where ghostly particles dance at the edge of existence, and where the laws of physics as we know them seem to bend and twist. It's a place so bizarre that even Einstein struggled to wrap his mind around it. And here's the wildest part. This invisible, intangible sea of energy might hold the keys to some of the biggest mysteries in the cosmos, from dark energy to the birth of universes. That's exactly what we're diving into today. Over the course of this journey, we'll uncover 30 of the most mind-bending mysteries hidden within the quantum vacuum. We'll explore how empty space could be teeming with infinite energy, how black holes might be siphoning secrets from this shadow realm, and even how the vacuum itself could be the reason our universe exists at all. This isn't just science, it's a frontier where the line between physics and philosophy blurs, where every answer leads to deeper, more thrilling questions. So if you're ready to peer into the hidden heart of reality, to see the universe in a way few ever have, let's begin. If you could zoom in on the so-called empty space between stars, down to scales so tiny they make atoms look gigantic, you'd witness something extraordinary. Particles flickering into existence out of nowhere, only to vanish again in an instant like cosmic fireflies blinking in and out of reality. This is the bizarre world of quantum fluctuations, where the vacuum isn't empty but alive with spontaneous bursts of energy. At the heart of this phenomenon lies Heisenberg's uncertainty principle, which tells us that on the smallest scales, nature refuses to sit still. Energy and time are locked in a cosmic dance. The more precisely you measure one, the less you can know about the other. This inherent fuzziness in reality means empty space can never truly be empty. Instead, it's a frothing sea of virtual particles, ghostly stand-ins for real matter that pop up in particle-antiparticle pairs, borrowing energy from the vacuum itself before vanishing back into nothingness. These fleeting particles aren't just theoretical curiosities. They shape the very fabric of our universe. Take something as ordinary as an atom. Why don't electrons simply spiral into the nucleus, collapsing matter as we know it? Quantum fluctuations create a kind of pressure that keeps them stable, like an invisible cushion preventing total collapse. On a grander scale, these same fluctuations might hold the key to one of cosmology's biggest puzzles, dark energy. Some theories suggest the vacuum's endless churn of particles could be driving the accelerated expansion of the universe, pushing galaxies apart with an unseen force. But here's the twist. When physicists try to calculate how much energy these fluctuations should contribute, the numbers are off by a factor of trillions. It's as if the universe is hiding most of its own energy from us, leaving scientists scrambling to solve what's called the vacuum catastrophe, the wildest part. These quantum hiccups might even rewrite our understanding of time. Imagine two metal plates placed incredibly close together in a vacuum. Normally, virtual particles of all wavelengths would flicker around them. But if the plates are close enough, only certain wavelengths can fit between them, creating a pressure imbalance. This bizarre effect, called the Casimir force, proves that quantum fluctuations aren't just math, they can push on objects in the real world. Some researchers speculate that if we could harness this vacuum energy, it might open doors to technologies straight out of science fiction, from warp drives to unlimited clean energy. Of course, that's still the stuff of dreams, but in the quantum vacuum, even dreams have a habit of flickering into reality. Now let's talk about the quantum vacuum's most baffling feature, zero-point energy. Even if you could cool space down to absolute zero, where all motion theoretically stops, the vacuum would still hum with energy. This isn't just a tiny background whisper, it's an infinite, roiling ocean of potential. The math suggests that every cubic centimeter of so-called empty space contains more energy than all the matter in the known universe combined. So why can't we just tap into it and solve all our energy problems forever? Here's where things get tricky. This energy isn't sitting there like a battery waiting to be used. It's chaotic, fleeting, and tied to those quantum fluctuations we just discussed. The particles popping in and out of existence borrow energy for such unimaginably short timescales that capturing it would be like trying to catch individual raindrops in a hurricane. That's why the dream of perpetual motion machines powered by zero-point energy remains pure science fiction. Nature's accounting is strict. Energy can't be created or destroyed, only borrowed and repaid with interest. The vacuum enforces its own kind of cosmic banking system, but that hasn't stopped brilliant minds from trying to harness even a fraction of this energy. Take Dutch physicist Hendrik Casimir, who predicted something astonishing in the 1940s. If you place two uncharged metal plates incredibly close together in a vacuum, they'll be pushed toward each other by an invisible force. Why, between the plates, only certain wavelengths of virtual particles can fit, while outside them particles of all wavelengths push in. The result: a measurable, real-world effect caused purely by the vacuum's energy. This Casimir effect isn't just a lab curiosity, it's proof that zero-point energy can influence physical objects, opening doors to nanotechnology and even quantum computing. Of course, where there's potential, there are also wild claims. Over the years, fringe inventors have declared breakthroughs in free energy, devices supposedly powered by zero-point energy. These machines often vanish as quickly as the virtual particles they claim to harness, either debunked as hoaxes or fading into obscurity when they fail to produce verifiable results. The harsh truth: extracting usable energy from the vacuum would require bending or breaking the very laws of thermodynamics that make our universe stable. If someone ever cracked that puzzle, they wouldn't just win a Nobel Prize, they'd rewrite physics itself. Yet the allure persists, and for good reason. Some theoretical models, like the Alcubierre warp drive, speculate that manipulating zero-point energy could one day distort space-time for faster-than-light travel. Others suggest it might explain dark energy's repulsive force, stretching the cosmos apart. For now, it remains locked in the quantum realm, a reminder that the universe's greatest treasures often come with riddles we're still learning to solve. Picture two perfectly smooth metal plates placed so close together in a vacuum that the gap between them is thinner than a strand of DNA. According to classical physics, nothing should happen, just empty space separating two inert objects. But in the quantum realm, something extraordinary occurs. The plates begin moving toward each other as if pulled by an invisible hand. This is the Casimir effect in action, one of the strangest and most concrete pieces of evidence that the vacuum is anything but empty. The secret lies in what's happening, or rather, not happening between those plates. Normally, the quantum vacuum buzzes with virtual particles of all possible wavelengths. But when the plates are brought extremely close together, only certain wavelengths can fit between them, like how only specific notes resonate inside a flute. Meanwhile, outside the plates, particles of all wavelengths continue their chaotic dance. The result: more virtual particles push inward on the plates than exist between them, creating a subtle but measurable force that pulls them together. It's as if the universe itself is pressing down on them, proving that empty space exerts real physical pressure. This phenomenon isn't just a laboratory oddity, it's a window into the bizarre properties of zero-point energy. The Casimir effect confirms that even in a perfect vacuum where all conventional energy has been removed, there's still an underlying hum of activity. Some researchers believe this energy could revolutionize nanotechnology. Imagine microscopic machines where components align themselves without physical contact, guided by the invisible push and pull of vacuum fluctuations. Already, engineers study Casimir forces to prevent tiny moving parts in nanoscale devices from sticking together unintentionally, a problem known as stiction. But the implications go even deeper. If nothingness can generate force, what does that say about the fabric of reality? Some theoretical physicists speculate that the same quantum pressure might play a role in the universe's expansion. Just as virtual particles push those metal plates, could they also be pushing galaxies apart on a cosmic scale? It's a tantalizing idea, though still far from proven. Even more radical is the notion that advanced civilizations might one day harness these effects not for perpetual motion, but for manipulating space-time itself. Theoretically, controlling vacuum energy could enable exotic propulsion systems or even warp drives, bending the rules of physics as we know them. Of course, for now, most of these ideas remain speculative. The Casimir force is incredibly weak, detectable only under precise conditions, yet its very existence shatters our classical intuition about emptiness. It's a reminder that the universe's most profound truths often hide in plain sight, or in this case, in the ghostly whispers between two metal plates. Now imagine the universe as a house of cards balanced precariously on a quantum ledge. What if all of existence, every star, every atom, even the laws of physics themselves, could vanish in an instant, erased by a single misstep in the fabric of reality? This isn't science fiction, it's vacuum decay, one of the most chilling possibilities in theoretical physics, and it all hinges on a question: is our universe sitting in a false vacuum? Think of the quantum vacuum like a valley. Right now, we're in what scientists call a false vacuum state, a stable-looking but potentially unstable low point in the energy landscape. The Higgs field, which gives particles their mass, holds this delicate balance in place. But here's the terrifying part: there might be a deeper, true vacuum state lurking beneath ours, like a hidden chasm. If the Higgs field were to suddenly tunnel into that lower energy state triggered by a random quantum fluctuation or even an experiment gone wrong, it could create a bubble of true vacuum. This bubble would expand at the speed of light, rewriting the fundamental laws of physics as it spreads. Atoms would disintegrate, forces would unravel. The universe as we know it would cease to exist, not with a bang, but with a quiet, inescapable rewrite of reality itself. Stephen Hawking called vacuum decay the ultimate environmental catastrophe. Unlike asteroids or supernova, there'd be no warning. One moment, everything's normal. The next, an invisible wall of annihilation races toward us, leaving no time to react. The irony: the very same quantum fluctuations that sustain existence could end it. Some calculations suggest the Higgs field is metastable stable for now, but not forever. Given enough time, trillions of years perhaps, a random quantum event might tip the scales. But here's where it gets stranger. If vacuum decay has already happened elsewhere in the cosmos, we wouldn't know. The bubble's edge would move at light speed, making it impossible to observe until it reached us. Some physicists speculate this could explain why we haven't detected advanced alien civilizations. If intelligent life inevitably tinkers with high-energy physics, maybe someone, somewhere, accidentally pressed the universe's self-destruct button. Yet there's a twist that softens the doom. The likelihood of vacuum decay is astronomically low. The universe has survived for 13.8 billion years without collapsing, suggesting our vacuum might be more stable than we fear. And if a bubble did form, it might not destroy everything. Some theories propose it would only alter certain constants, leaving a new, stranger universe in its wake, one where life, if it could exist at all, would play by entirely different rules. So is vacuum decay a real threat or just a brain-bending thought experiment? For now, it's both a reminder of how fragile reality might be and a testament to the audacity of physics where even nothingness holds the power to undo everything. But what if the quantum vacuum isn't just shaping tiny metal plates or flickering particles? What if it's stretching the entire cosmos apart? This is where things get truly cosmic. For decades, astronomers have known the universe isn't just expanding, it's accelerating, as if some invisible force is pushing galaxies away from each other faster and faster. They call this force dark energy, and here's the twist: the quantum vacuum might be its source. At first glance, it makes perfect sense. If empty space is teeming with zero-point energy, that energy should exert a kind of pressure, a repulsive force that could drive cosmic expansion. In fact, this idea goes all the way back to Einstein, who first proposed a cosmological constant to balance the universe against gravity's pull. He later called it his greatest blunder, but modern physics has revived the concept with a vengeance. The quantum vacuum's energy density should act like Einstein's constant, an anti-gravity effect woven into spacetime itself. But here's where the story takes a sharp turn. When physicists calculate how much energy the quantum vacuum ought to contribute based on particle physics, the numbers are catastrophically wrong. Not just off by a little, off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. To put that in perspective, it's like predicting a candle's brightness but getting an answer brighter than a billion supernovas. This mismatch isn't just embarrassing, it's the widest gap between theory and observation in all of science, earning it the title of the worst prediction in physics. Why such a colossal discrepancy? One possibility is that we're missing something fundamental, a symmetry or cancellation principle that nullifies most of the vacuum's energy. Some theories, like supersymmetry, propose undiscovered particles that could balance the equation, but so far, no evidence has turned up. Others suggest the vacuum's energy might be dynamic, changing over time rather than being a fixed constant. Then there's the radical idea that dark energy isn't vacuum energy at all, but something entirely different, a new field or a flaw in our understanding of gravity. The stakes couldn't be higher. If the quantum vacuum is driving cosmic acceleration, its energy density determines the universe's ultimate fate. Too much, and galaxies will eventually rip apart in a big rip. Too little, and gravity might yet reignite a collapse. For now, the cosmological constant problem remains one of physics' deepest mysteries, a reminder that even the emptiest corners of space hold secrets capable of rewriting our understanding of reality. Black holes have long been seen as cosmic vacuum cleaners, swallowing everything that crosses their event horizons, even light itself. But what if these gravitational monsters aren't just consuming the universe? What if they're also leaking, slowly dissolving back into the quantum foam from which they came? This mind-bending possibility comes from one of Stephen Hawking's greatest insights. Black holes can actually evaporate thanks to the strange interplay between gravity and the quantum vacuum. Here's how it works. At the very edge of a black hole's event horizon, the gravitational pull is so intense that it warps the fabric of spacetime itself. In this twisted region, the quantum vacuum gets stretched and squeezed, creating tiny ripples in reality. Remember those virtual particle-antiparticle pairs that constantly flicker in and out of existence? Near a black hole, something extraordinary happens. One particle gets sucked into the abyss while the other escapes, stealing a tiny bit of the black hole's energy in the process. To an outside observer, it looks like the black hole is emitting radiation now called Hawking radiation. Over unimaginable timescales, this steady trickle of particles drains the black hole's mass until eventually it vanishes in a final burst of energy. But this elegant idea comes with cosmic paradoxes. If a black hole evaporates, what happens to all the information it swallowed? Quantum mechanics insists that information can't be destroyed. It might get scrambled, but it should always be recoverable in principle. Yet Hawking's original calculations suggested the radiation emitted would be random, carrying no trace of the star, planet, or unlucky spaceship that fell in. This contradiction, known as the black hole information paradox, has kept physicists arguing for decades. Some propose the information gets encoded in the radiation after all, like a cosmic hologram. Others suggest it might be trapped in a hidden remnant or even escape into a parallel universe. The debate is so heated that Hawking himself famously changed his mind, eventually conceding that information probably isn't lost, though we still don't know how it escapes. The implications stretch far beyond black holes. If Hawking radiation is real, it means even the darkest corners of the universe obey the laws of thermodynamics. Black holes aren't just gravitational pits, they have temperature and entropy, behaving like bizarre celestial objects with their own rules of heat and energy. A supermassive black hole, for instance, emits so little Hawking radiation that it would take longer than the current age of the universe to evaporate. But a tiny, mountain-sized black hole, it would glow fiercely, radiating away its mass in a matter of seconds. Some scientists speculate that if such mini black holes were created in the early universe, we might still detect their explosive deaths as gamma-ray flashes in the night sky. And here's the ultimate twist. Hawking radiation suggests that black holes aren't eternal. Given enough time, far longer than trillions of years, every black hole in the cosmos could fade away, leaving behind only a whisper of radiation in an otherwise empty universe. It's a humbling thought. Even the mightiest objects in existence are subject to the quantum vacuum's subtle power, a reminder that nothing, not even spacetime's darkest secrets, can escape the rules written into the fabric of reality. Einstein once called it spooky action at a distance, the idea that two particles could be so deeply linked that changing one instantly affects the other, no matter how far apart they are. This bizarre phenomenon, known as quantum entanglement, lies at the heart of the EPR paradox, a thought experiment so unsettling it made even the pioneers of quantum mechanics question their own theories. Picture two electrons created together in the quantum vacuum. According to quantum rules, they can become entangled, their properties perfectly correlated even if separated by light years. Measure one's spin as up, and the others will always be down instantaneously, as if they're whispering secrets faster than light itself. Einstein, Podolsky, and Rosen argued in 1935 that this violated locality, the principle that nothing can influence anything else faster than light can travel between them. They believed quantum mechanics must be incomplete, hiding unseen variables that predetermine the particle states. But decades later, physicist John Bell proved something extraordinary. His theorem showed that if quantum mechanics were correct, entangled particles would display correlations stronger than any hidden variable theory could explain. The kicker: experiments confirmed Bell's predictions. When scientists measured entangled particles, their results matched quantum mechanics perfectly, leaving no room for Einstein's hidden variables. The vacuum wasn't just hosting these strange connections, it was enabling them. This isn't just theoretical sleight of hand. Quantum teleportation experiments have harnessed entanglement to transmit information across labs, cities, even between satellites and Earth. In 2017, Chinese scientists sent entangled photons from space to ground stations over 700 miles apart, and the particles still behaved as one. The implications are staggering. If information isn't traveling between them, how do entangled particles know what their partners are doing? Some interpretations suggest the universe isn't as separate as it seems, that at a fundamental level, everything is interconnected through the quantum vacuum, with distance itself being an illusion. Yet the debate rages on. Could there be loopholes in Bell's theorem? Some argue that detectors might miss subtle correlations or that particles influence each other through hidden dimensions. Others propose retrocausality, that future measurements somehow reach back to alter past states. What's clear is that the vacuum's role in entanglement defies classical intuition. It's not just empty space mediating these connections. It's an active participant, a stage where the rules of cause and effect blur into something far stranger. Whether you call it spooky action or profound physics, one thing's certain: the quantum vacuum holds mysteries that still challenge our deepest assumptions about reality. Imagine an electron orbiting an atom's nucleus, picture perfect, like a tiny planet circling a sun. Now, here's the catch: that electron isn't moving through empty space. It's swimming through a chaotic sea of quantum fluctuations, and those ghostly flickers in the vacuum are nudging it ever so slightly off course. This minuscule deviation, barely perceptible even to our most precise instruments, is called the Lamb shift. And its discovery didn't just tweak our understanding of atoms, it reshaped the entire landscape of modern physics. Willis Lamb and his colleague Robert Rutherford uncovered this anomaly in 1947, probing hydrogen atoms with microwave radiation. According to Paul Dirac's then-dominant quantum theory, electrons in hydrogen should occupy certain fixed energy levels, but Lamb's meticulous measurements revealed a tiny split between two states that should have been identical, like finding a phantom step between floors of a building that was supposed to be perfectly level. The difference was vanishingly small, just 1 part in a million, but it sent shockwaves through the physics community. Here was hard evidence that the vacuum itself was subtly altering reality, confirming predictions from the fledgling theory of quantum electrodynamics, or QED. The genius of QED lies in how it explains this effect. In this framework, the electron isn't just an isolated particle, it's constantly exchanging virtual photons with the quantum vacuum, a frenetic dance that slightly changes its energy. Think of it like walking against a strong wind. Even if you're trying to move straight ahead, the gusts push you off balance. Those virtual photons are the cosmic wind, buffeting the electron and causing its orbit to shift. What makes this so revolutionary is that it wasn't just a theoretical idea. The Lamb shift gave physicists a measurable, tangible fingerprint of vacuum fluctuations, proof that empty space was alive with invisible activity. But the story doesn't end there. This discovery became a crucial testing ground for QED, which was still viewed with skepticism by some of the era's greatest minds, including Einstein. When theorists like Julian Schwinger and Richard Feynman calculated the Lamb shift using their radical new methods, their predictions matched LAMB's Chinese letter to an astonishing degree, some say to within the width of a hair compared to the distance across the United States. This precision didn't just validate QED, it showcased the power of quantum field theory, elevating it from a controversial idea to the cornerstone of particle physics. Today, the Lamb shift is more than a historical footnote. It's a reminder that even the most fundamental aspects of nature, like the motion of an electron, are shaped by the unseen turmoil of the quantum vacuum. From atomic clocks to quantum computing, technologies that rely on ultra-precise measurements must account for these vacuum effects. And cosmically, if vacuum fluctuations can tweak something as small as an electron's orbit, imagine their role in the grand tapestry of the universe. The Lamb shift is a whisper from the quantum void, telling us that nothing, no matter how seemingly static, escapes the restless churn of reality's hidden depths. What happens when you accelerate through empty space? You might expect to feel only the weight of your own motion, but according to quantum physics, you'd also step into a shower of particles that weren't there before. This is the Unravel effect, a mind-bending prediction where the vacuum itself seems to light up for an accelerating observer while remaining utterly dark for someone standing still. Picture an astronaut floating in what appears to be perfect emptiness. Suddenly, their ship's engines fire, thrusting them forward, As they accelerate, their instruments begin detecting faint traces of heat, not from the ship but from space itself. To them, the vacuum has transformed into a warm bath of radiation. Yet, if a second astronaut nearby remains at rest, they'll measure nothing but cold, empty void. Both observers are correct, and neither is hallucinating. Reality itself depends on how you're moving through it. This phenomenon hinges on one of relativity's core ideas. There's no privileged frame of reference. Einstein taught us that motion is always relative whether you're at rest or gliding at constant velocity. The laws of physics stay the same, but acceleration. That changes everything. When you push through space fast enough, the quantum vacuum behaves differently depending on your state of motion. For the accelerating observer, virtual particles that usually flicker in and out of existence too quickly to detect get stretched into real, measurable particles by the sheer force of their motion. It's as if the vacuum's hidden energy gets spun up into visibility, much like how friction heats a meteor streaking through the atmosphere. The faster the acceleration, the hotter this phantom radiation becomes, though for any human survivable forces, the effect would produce temperatures colder than the deepest reaches of space. The parallels to Hawking radiation are uncanny. Just as an accelerating observer detects particles where none existed before, a black hole's intense gravity, acting like relentless acceleration, creates the same eerie glow at its event horizon. Both effects reveal how motion and gravity can coax reality from seeming nothingness, blurring the line between particles and the empty space they emerge from. Some physicists argue this isn't just a coincidence but a clue to a deeper truth. Particles might not be fundamental at all. Instead, they could be artifacts of how we interact with the quantum vacuum, like ripples in a pond that only exist when something disturbs the water. Yet the Unravel effect remains one of quantum theory's most hotly debated predictions. Why? We've never observed it directly. The radiation only becomes noticeable at accelerations so extreme they'd pulp a human body. Think falling into a black hole or riding a hypothetical cosmic catapult. Even the most powerful particle accelerators on Earth can't muster the needed forces. Some theorists propose workarounds, like using ultra-sensitive detectors or mimicking acceleration with clever lab setups, but so far, no experiment has captured the effect beyond statistical hints in quantum simulations. Skeptics argue this makes the Unravel effect more philosophical than physical, a tantalizing idea that might never leave the realm of equations. But even unproven, its implications ripple through physics. If reality looks different depending on how you move, does that mean particles are illusions? Could the universe's building blocks be, at their core, just relationships between observers and the vacuum? The Unravel effect doesn't just challenge our intuition. It suggests that existence itself might be a kind of cosmic theater, where the actors only appear when the audience is moving fast enough to see them. And that raises a haunting question. What else is hiding in the vacuum, waiting for the right motion to bring it into being? Imagine trying to measure the exact strength of a magnet, only to find its power subtly shifts the closer you look, not because the magnet is changing, but because the very space around it is alive with invisible interference. This is the essence of vacuum polarization, a phenomenon where the quantum vacuum's seething sea of virtual particles bends and warps electromagnetic forces in ways that defy classical intuition. At its core, it's a cosmic game of hide and seek. When an electron emits a photon, that photon doesn't travel through empty space. Instead, it plows through a storm of virtual particle-antiparticle pairs, electrons and positrons flickering in and out of existence. These fleeting particles act like microscopic mirrors, reflecting and distorting the photon's path. To the original electron, it's as if its own electric charge has been partially obscured or screened by this quantum static. The implications are profound. In quantum electrodynamics, this screening effect forces physicists to confront infinity's mathematical divergences that arise when calculating simple quantities like an electron's charge or mass. Enter renormalization, the brilliant but controversial trick that salvages the equations. By acknowledging that the bare values of these properties are impossible to isolate from the vacuum's influence, theorists can subtract the infinities, leaving behind finite, measurable results. It's like trying to weigh a fish in a swimming pool. The water's buoyancy alters the scale, so you must account for it to find the fish's true weight. Renormalization does the same for particles, separating the vacuum's noise from their intrinsic properties. But vacuum polarization isn't just a mathematical band-aid, it leaves fingerprints in the real world. Take the electron's magnetic moment, a measure of how strongly it interacts with magnetic fields. Dirac's original prediction was off by about 0.1%, a tiny but stubborn discrepancy. Why? The vacuum's polarizing effect subtly tweaks the electron's behavior, like a dancer nudged off rhythm by gusts of wind. When theorists included vacuum polarization in their calculations, the numbers aligned with experiments to an astonishing precision, 12 decimal places, making it one of the most stringently tested predictions in science. The wildest twist, this effect isn't limited to electrons. In extreme environments like heavy ion colliders, where atomic nuclei smash together at near light speeds, vacuum polarization can temporarily strengthen electromagnetic forces. The immense energy tears virtual particles from the vacuum, transforming them into a plasma that amplifies charges, a phenomenon called charge shielding reversal. It's as if the quantum vacuum under pressure flips its own rules. From the infinitesimal to the cosmic, vacuum polarization reminds us that nothing in the universe acts in isolation. Even the simplest force is a collaboration between particles and the hidden turbulence of empty space, a turbulence so precisely choreographed that it's written into the very fabric of reality. And every time we measure an electron's spin or a photon's path, we're glimpsing the universe's most intimate conversation, whispered between the seen and the unseen. Even the most powerful electric fields in everyday life, lightning, the spark from a doorknob, leave the quantum vacuum untouched, but crank that field up to unimaginable levels and something astonishing happens. The void itself begins to crack, spitting out pairs of real particles like cosmic sparks leaping from empty space. This is the Schwinger effect, named after physicist Julian Schwinger, who predicted that a strong enough electric field could rip the vacuum apart, tearing matter directly from nothingness. Here's how it works. Normally, when a virtual electron-positron pair flickers into existence, they're doomed to annihilate each other almost instantly, like two phantoms passing in the night. But introduce an electric field of around 10 to the power of 18 volts per meter, a strength that makes the heart of a supernova look tame, and something changes. The field yanks the electron and positron in opposite directions before they can collide, supplying the energy needed to promote them from fleeting ghosts to real, detectable particles. It's as if the vacuum, stretched thin by the field's force, finally snaps like an overstretched rubber band, leaving behind tangible fragments of reality. This isn't just theoretical. Some of the universe's most extreme environments might be running this experiment naturally. Take pulsars rapidly spinning neutron stars with magnetic fields trillions of times stronger than Earth. Near their poles, the intense electromagnetic fields could generate particle pairs via the Schwinger effect, fueling the star's glowing auroras and radio pulses. Even black holes might participate. In the chaotic regions around their event horizons, tidal forces could create fields strong enough to pull particles from the vacuum, adding a new twist to Hawking radiation. On Earth, we're tantalizingly close to testing Schwinger's prediction directly. Ultra-intense laser facilities, like the European Extreme Light Infrastructure, can now produce pulses with fields approaching the required threshold. By focusing multiple lasers onto a single point in a vacuum chamber, physicists hope to spot the telltale spark of electron-positron pairs materializing from pure energy. The challenge: distinguishing Schwinger pairs from the noise of conventional particle collisions. Some teams propose looking for a unique signature particles born with specific energies that betray their quantum origins. But here's the real kicker. The Schwinger effect blurs the line between matter and empty space. If we can conjure particles from the void, doesn't that suggest the vacuum is less a static stage and more a dynamic participant in creation? It's a reminder that even in physics, the most profound breakthroughs often come not from asking what exists, but from probing what nothingness can become when pushed to its limits. In the early days of quantum mechanics, physicist Paul Dirac stared into the equations describing electrons and saw something no one else had noticed, a paradox so troubling it threatened to unravel the entire theory. His equations predicted that electrons shouldn't just have positive energy states we observe, but also an infinite ladder of negative energy states. If true, this meant every electron in the universe should spontaneously tumble down this ladder, releasing infinite energy as it fell, a cosmic catastrophe that clearly wasn't happening. Rather than dismiss this as a mathematical quirk, Dirac proposed something radical. What if all those negative energy states were already occupied? Picture an ocean so vast and dense that it fills the entire universe, with every drop representing an electron lurking in a negative energy state. This is the Dirac Sea, a hidden, infinite reservoir of particles too deep to detect directly. According to his idea, what we perceive as empty space is actually this sea, completely filled like a theater with every seat taken. When an electron in the sea gets enough energy, say, from a gamma ray, it can leap up into a positive state, leaving behind a hole in the sea. That hole, Dirac realized, would behave exactly like an electron with opposite charge, the first prediction of antimatter. The elegance was breathtaking. Dirac Sea not only solved the negative energy paradox, but also foreshadowed the discovery of positrons, which were found just 4 years later in cosmic ray experiments. Yet for all its brilliance, the sea metaphor had flaws. An infinite ocean of particles implied an absurdly large total mass and charge for the vacuum properties that should warp spacetime in ways we'd easily notice. Worse, it couldn't explain particles like photons that don't obey the same exclusion rules as electrons. Quantum field theory swept these problems aside by reimagining the vacuum entirely. Instead of a static sea, modern physics describes virtual particles as temporary disturbances in quantum fields, like waves rising and falling on an invisible ocean. Antimatter isn't a hole in a sea, but a genuine particle in its own right, born from the same field as matter. The Dirac Sea's intuition about antimatter proved correct, but its underlying mechanics were like Newton's gravity, a useful approximation overshadowed by a deeper truth. Still, Dirac's idea left an indelible mark. It showed how confronting paradoxes head-on could lead to revolutionary insights, even if the original framework needed reworking. Today, remnants of the sea live on in concepts like Fermi levels in material science, where electron behavior mirrors Dirac's filled states. And for all its inaccuracies, the image of a churning, particle-filled vacuum resonates with our modern understanding, not as a literal sea, but as a dynamic void where particles and antiparticles constantly dance on the edge of existence. Light passing through a crystal splits into two beams, an ordinary ray and an extraordinary one, each bending at slightly different angles. This property, called birefringence, is how calcite crystals create dazzling double images. But what if the vacuum itself could do the same? Under the grip of cosmic strength magnetic fields, empty space isn't so empty anymore. It transforms into an ethereal crystal, bending light in ways that defy intuition. Welcome to vacuum birefringence, where the quantum vacuum becomes an optical prism writ large across the universe. This phenomenon emerges from the quantum dance between light and virtual particles. Normally, photons zip through the vacuum unimpeded, but place them near a magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth's, and everything changes. The field stretches the vacuum's virtual electron-positron pairs into tiny, ghostly antennas that interact differently with light depending on its polarization. Photons oscillating parallel to the field's lines slow slightly, while those vibrating perpendicularly move faster. The result, a beam of light splits as if passing through an invisible cosmic gem. The first hints of this effect came not from telescopes but from math. Quantum electrodynamics predicted vacuum birefringence decades ago, but testing it seemed impossible, until astronomers turned their gaze to neutron stars. In 2016, the European Space Agency's XMM Newton telescope spotted polarized X-rays from the magnetar 1e 2259.5418. The light's polarization angles aligned precisely with QED's predictions, as if the star's crushing magnetic field had scribbled quantum equations across the sky. What makes this discovery so revolutionary? It's a direct window into the vacuum's texture. Just as geologists learn about Earth's interior by studying seismic waves, physicists probe the quantum void by watching how light twists through extreme fields. Future observations could push QED to its limits, searching for deviations that might hint at new particles or forces lurking in the vacuum's depths. And if we ever harness such fields in the lab, perhaps with next-generation lasers, we might recreate this cosmic alchemy, turning empty space into a lens that bends reality itself. From neutron stars to equations on a chalkboard, vacuum birefringence reminds us that even nothingness has structure, a hidden architecture waiting to reveal itself under the right conditions. And when it does, it doesn't just bend light, it bends our understanding of what emptiness truly means. At scales a billion trillion times smaller than an atom, space-time itself stops behaving like the smooth fabric Einstein imagined. Instead, it seethes with a turbulent froth, a chaotic, bubbling foam where the very concepts of here and now lose all meaning. This is quantum foam, physicist John Wheeler's radical vision of reality's foundation, where space-time isn't a stage but a boiling ocean of uncertainty. Picture it like the surface of a carbonated drink, with tiny bubbles of distorted geometry constantly forming and popping into existence. But unlike soda fizz, these bubbles aren't made of gas, they're fluctuations in the fabric of reality itself, where wormholes might blink open and shut, and miniature black holes evaporate before they can be measured. Wheeler proposed this dizzying idea in the 1950s, arguing that at the Planck scale, distances of around 10 to the power of -35 meters, quantum mechanics and general relativity collide violently. Gravity's grip becomes so strong that it warps spacetime into unpredictable, fractal-like structures. One moment, a region might resemble a tiny black hole. The next, it could stretch into a microscopic wormhole bridging 2 points in the foam. These aren't the stable cosmic tunnels of science fiction, but fleeting ripples in the quantum turbulence, lasting mere fractions of a second. Yet their existence hints at something profound. Space-time might not be fundamental but emergent, a statistical average of this deeper, wilder reality beneath. The implications shatter our classical intuition. If space-time is foamy, then the vacuum isn't just hosting particles, it's constantly rewriting the rules of geometry. Light traveling across the cosmos wouldn't glide smoothly but stutter step through this froth, accumulating tiny deviations that could blur distant starlight. Some theories suggest this effect might already be visible in gamma-ray bursts, where the highest energy photons arrive slightly later than their lower energy counterparts, as if fighting through an invisible cosmic sieve. Others propose that quantum foam could leave fingerprints in gravitational wave detectors, with spacetime's graininess whispering through the ripples from colliding black holes. Yet the foam remains maddeningly elusive. Probing Planck-scale physics directly would require accelerators the size of galaxies or sensors smaller than anything we can build. Even nature's most energetic particle collisions, cosmic rays slamming into the atmosphere with the force of a fastball, only graze the edges of this realm. For now, the foam lives in equations and thought experiments, a reminder that beneath the universe's apparent order lies a turbulence we're only beginning to map. Whether it's the seed of wormholes, the key to quantum gravity, or just another layer of the vacuum's infinite mystery, one thing's certain: reality's foundations are far stranger than they appear. What if the entire universe, every galaxy, every atom, even the space between them, was nothing more than an elaborate hologram? Not a literal screen, but a projection of information encoded on some distant, two-dimensional surface. This mind-melting idea is the holographic principle, and it suggests that the quantum vacuum might be more than just empty space. It could be the canvas upon which reality itself is painted. The story begins in the 1970s with a young physicist named Jacob Bekenstein. While studying black holes, he made a startling discovery. A black hole's entropy, a measure of its hidden information, wasn't proportional to its volume as you'd expect, but to its surface area. It was as if all the data about what fell into the black hole wasn't stored inside but smeared across its event horizon like cosmic ink. Stephen Hawking later confirmed this with his own calculations, showing that black holes radiate information as they evaporate, hinting that the universe might keep its accounts on surfaces, not in volumes. Fast forward to the 1990s, when physicist Gerard T. Hooft and string theorist Leonard Susskind took this idea even further. If black holes store information on their boundaries, they argued, maybe the entire universe does the same. Imagine a closed room with walls made of infinitesimally tiny pixels. According to the holographic principle, everything happening inside that room, every particle collision, every ripple of light, could be encoded on those walls. The 3D world we experience would just be a projection of that 2D data, like a movie playing on the walls of a cosmic theater. String theory gave this wild notion a mathematical backbone. In 1997, Juan Maldacena discovered the AD-S/CFT correspondence, a concrete example of holography in action. His equations showed that a hypothetical universe with gravity, a bulk space, could be perfectly described by a quantum field theory living on its boundary without gravity at all. Think of it like a one-to-one translation between two completely different languages: the 3D world of space-time and the 2D world of quantum information. Suddenly, the vacuum's deepest mysteries, its entropy, its fluctuations, might just be shadows of a deeper, flatter reality. But how could this possibly work in our universe? If we're living in a hologram, where's the screen? Some theorists suggest it's at the edge of the observable cosmos, the spherical boundary of our expanding pocket of space-time. Others propose it's woven into the fabric of the quantum vacuum itself, with every Planck-sized patch of space encoding bits of information like a cosmic hard drive. Either way, the implications are staggering. Dark energy, the uniformity of the cosmic microwave background, even the very nature of gravity, all might emerge from this informational substrate, like ripples on a pond emerging from the motion of invisible water molecules. Skeptics argue that without direct experimental proof, holography remains a beautiful but unproven metaphor. Yet tantalizing clues are emerging. Some versions of the theory predict subtle blurring in distant starlight, an effect that could be tested with next-generation telescopes. Others suggest that quantum entanglement, which connects particles across vast distances, might be the glue stitching the holographic illusion together. Whether the universe is truly a hologram or not, one thing's clear: the quantum vacuum isn't passive. It might be the most active, information-rich frontier we've ever dared to explore. Why is there something rather than nothing? It's one of philosophy's oldest questions, but in the quantum vacuum, it becomes a concrete physics puzzle. Look around and you'll see a universe made of matter, stars, planets, even your own hands. But according to everything we know about particle physics, the Big Bang should have created equal amounts of matter and antimatter, leaving them to annihilate each other in a flash of pure energy. So why does anything exist at all? The answer might lie in the vacuum's hidden asymmetries, a set of conditions first proposed by Soviet physicist Andrei Sakharov that turned nothingness into a cosmic assembly line for matter. Sakharov's brilliance was in identifying three crucial ingredients needed to cook up a matter-dominated universe. First, you need a process that violates baryon number, a rule that normally prevents protons and neutrons from appearing or disappearing at will. Second, there must be a violation of something called CP symmetry, which ensures particles and their mirror image antiparticles behave identically. And third, these processes can't happen in equilibrium. They need the out-of-balance conditions of the early universe's rapid expansion. The quantum vacuum provides the perfect stage for this drama. In the seething turbulence just after the Big Bang, virtual particles popping in and out of existence might have tipped the scales ever so slightly toward matter. Here's where things get wild. In 1967, experiments with decaying kaons, exotic particles made of strange quarks, revealed the first hard evidence of CP violation. These particles broke the mirror image rule, decaying into matter slightly more often than antimatter. Later studies of B mesons confirmed the effect, proving Sakharov was onto something. But the observed asymmetry is tiny, just 1 part in a billion. That's not nearly enough to explain the overwhelming matter surplus we see today. So where's the rest of the imbalance hiding? Some theorists suspect the answer lurks in the vacuum itself. One compelling idea involves hypothetical particles called leptoquarks, which could have interacted with the Higgs field in the early universe, creating a feedback loop that amplified matter production. Others point to electroweak baryogenesis, where phase transitions in the vacuum like cosmic-scale versions of water, freezing into ice-generated bubbles where matter briefly dominated. The real kicker, these processes might still be detectable. Gravitational wave observatories could one day spot ripples from those primordial phase transitions, while particle colliders might create leptoquarks in high-energy crashes. The beauty of Sakharov's conditions is how they transform the vacuum from a passive backdrop into an active sculptor of reality. Those fleeting quantum fluctuations didn't just tweak the universe's balance sheet, they wrote it, turning a potential sea of pure radiation into a cosmos brimming with galaxies, planets, and life. It's a reminder that even the tiniest asymmetry in nothingness can cascade into everything we know. Imagine tuning a radio to an empty frequency. Instead of static, you hear a perfect, steady hum. That's the quantum vacuum's baseline noise, a fundamental hiss woven into the fabric of reality. But what if you could twist that noise like putty, suppressing it in one direction while amplifying it in another? This isn't science fiction, it's vacuum squeezing, a quantum trick that lets us redistribute uncertainty itself. At the heart of this phenomenon lies Heisenberg's famous principle. The more precisely you measure a particle's position, the fuzzier its momentum becomes, and vice versa. It's a cosmic balancing act, but squeezed states tilt the scales. By manipulating quantum fields, physicists can quiet noise in one variable, say, an electric field's amplitude, while letting it run wild in another, like its phase. Picture squeezing a balloon. As one side shrinks, the other bulges. The total uncertainty stays the same, but now it's strategically reshaped. This delicate control unlocks revolutionary tools. Gravitational wave detectors like LIGO use squeezed light to peer deeper into the cosmos. Normally, quantum noise would drown out faint ripples from colliding black holes billions of light years away. But by injecting light squeezed in amplitude, LIGO lasers reduce uncertainty in timing measurements, boosting sensitivity by up to 50%. It's like turning down the hiss on a microphone to catch whispers across a stadium. Quantum computing takes this even further. Qubits, the fragile building blocks of quantum processors, are easily disturbed by vacuum fluctuations. Squeezed states act as noise-canceling headphones for quantum information, protecting delicate operations from decoherence. Recent experiments trapped ions in squeezed electromagnetic fields, extending their coherence times tenfold. Some theorists even speculate that advanced squeezing could enable error-proof quantum communication, teleporting data across networks with near-perfect fidelity. The real magic lies in how we achieve this control. One method involves firing lasers through special crystals that convert incoming photons into entangled pairs. These pairs interfere in ways that redistribute quantum noise, effectively pushing uncertainty where we don't need precision. Another approach uses superconducting circuits to engineer synthetic vacuums, tweaking their electromagnetic properties to favor specific variables. Yet squeezed light isn't just a laboratory curiosity, it might be everywhere. Some models suggest the early universe's rapid expansion could have cosmically squeezed quantum fields, leaving imprints in the cosmic microwave background. If so, the vacuum's subtle asymmetries could hold clues to the Big Bang itself. From black hole collisions to the birth of spacetime, squeezing proves that even nothingness can be sculpted, and in its twists we might just find the universe's deepest secrets. Before Einstein rewrote physics, scientists believed space was filled with an invisible substance called the luminiferous ether, a static medium through which light waves traveled, much like sound needs air. This ether was supposed to be the ultimate reference frame, the unmoving backdrop of the universe. But in 1887, Albert Michelson and Edward Morley set out to detect it with an experiment so precise it could measure the flutter of a butterfly's wing. They split a beam of light, sent the halves racing perpendicular to each other, and expected the ether's flow to delay one beam like swimmers fighting a current. The result, nothing, no delay, no drift, no ether. Their failed experiment became one of science's greatest triumphs, proving the ether didn't exist. Or did it? Fast forward to today, and the quantum vacuum bears an eerie resemblance to that discredited ether. It's everywhere, it influences light and matter, and it even has measurable effects like the Casimir force. But here's the critical difference. The vacuum isn't a medium, it's the absence of one. The old ether was imagined as a fixed stage, a cosmic molasses that light struggled through. The quantum vacuum, though, is dynamic, alive with fluctuations that defy any static reference frame. Where the ether would have dragged light like wind slows a runner, the vacuum's particles flicker symmetrically, leaving light's speed untouched. This distinction matters because it shows how deeply our metaphors shape science. The ether was a 19th century idea, born from the need to explain waves without a medium. But the quantum vacuum is a 20th century revelation emerging from the math itself, an entity that doesn't just allow particles to exist but defines their existence. Michelson and Morley's null result didn't just kill the ether, it paved the way for relativity, where space and time bend, and the vacuum's energy becomes spacetime's ink. Yet the ghost of the ether lingers in language. We still say light travels through the vacuum as if it's a substance. Physicists even debate whether the Higgs field, which fills space and gives particles mass, is a spiritual successor to the ether. But the Higgs isn't a medium, it's a quantum field with no preferred direction, no drag. The vacuum's lesson is clear: reality doesn't need an ether. It needs something far stranger, a nothingness that's everywhere, doing everything while remaining at its core perfectly, profoundly empty. Engineered materials are beginning to bend the rules of reality in ways that mimic the quantum vacuum's strangest behaviors, giving scientists an unprecedented playground to test theories that were once purely hypothetical. Take negative refraction, for example. In nature, light always bends at predictable angles when passing between materials, like a straw appearing to bend in a glass of water. But metamaterials, synthetically structured composites, can flip this effect upside down. By arranging microscopic structures in precise geometric patterns, researchers have created materials that refract light backward, essentially reversing Snell's law. This isn't just a parlor trick. Negative refraction mirrors how light might behave in the distorted spacetime near a black hole or in the extreme conditions of the quantum vacuum, where virtual particles warp the path of photons in counterintuitive ways. One of the most striking applications of these vacuum-inspired designs is optical cloaking. Just as the vacuum's fluctuations can hide particles from direct observation, metamaterials can redirect light around an object, rendering it invisible to specific wavelengths. Early prototypes used layered rings of copper and fiberglass to steer microwaves around a central cavity like water flowing around a rock, while more advanced designs aim to achieve visible light cloaking. The catch, perfect invisibility, would require materials that manipulate every wavelength simultaneously, a challenge akin to tuning a radio to every station at once. Yet even partial cloaking has revolutionary potential, from medical imaging that peers through tissue without scattering to stealth technologies that vanish from radar. Then there's the artificial Casimir effect. Normally, this quantum force arises from vacuum fluctuations between two plates, but metamaterials can simulate it using carefully structured surfaces that mimic the vacuum's electromagnetic constraints. In labs, scientists have built nanostructured silicon membranes that replicate the Casimir attraction, or even reverse it, creating repulsion. This isn't just a curiosity. It could solve real-world problems like stiction in microelectromechanical systems, where tiny components stick together due to microscopic forces. By tailoring these designer vacuums, engineers might one day create frictionless nanomachines or even anti-gravity-like effects on demand, the ultimate goal. A material that fully emulates the quantum vacuum's energy density, a so-called perfect lens that could focus light beyond the diffraction limit, revealing details smaller than a wavelength. Imagine a microscope that sees individual viruses with optical clarity, or a solar cell that harvests energy from usually wasted infrared light. While we're not there yet, each breakthrough blurs the line between the quantum void and the materials we can hold in our hands. These metamaterials don't just copy the vacuum's tricks, they're teaching us how to rewrite the rules of physics itself. It's the most embarrassing number in physics. A discrepancy so vast it makes every other measurement error in history look like a rounding glitch. The quantum vacuum should contain enough energy to rip space-time apart 1 trillion times over, yet somehow our universe remains perfectly habitable. This is the vacuum catastrophe, the jaw-dropping gap between theory and observation, where calculations overshoot reality by 120 orders of magnitude. To put that in perspective, it's like predicting a single grain of sand could outweigh the entire observable universe. So where did the math go so wrong? The problem starts with virtual particles. Every cubic centimeter of empty space seethes with these fleeting entities, each contributing a tiny bit of energy. Sum them all up, and the total should be enormous enough to curve space-time into a black hole the size of a pinhead. But when astronomers measure the actual energy density of the vacuum using cosmic expansion rates, they find a value so small it's practically zero. It's as if nature's accounting has a hidden ledger, canceling out nearly all this energy behind the scenes. Desperate for answers, physicists have proposed some radical fixes. Supersymmetry, a beloved but still unproven theory, suggests every known particle has an undiscovered twin. These superpartners could cancel out the vacuum's energy contributions, balancing the books perfectly. The catch, after decades of searching, colliders like the LHC have found zero evidence these particles exist. Then there's the anthropic principle, the controversial idea that our universe's vacuum energy is low because we're here to observe it. In a multiverse where most bubbles have lethal energy densities, we simply live in the rare one where life is possible. It's a philosophical shrug, not a predictive theory, but some argue it's the only explanation that fits. But what if the problem runs deeper? Maybe Einstein's cosmological constant, the term he added to general relativity to keep the universe static, isn't a constant at all. Some theories propose vacuum energy changes over time, starting high during inflation before decaying to today's whisper. Others suggest gravity behaves differently on cosmic scales, with modifications to general relativity diluting the vacuum's impact. The boldest idea, that quantum field theory itself is flawed, that we're missing a principle as fundamental as relativity that would resolve the catastrophe at its roots. The stakes couldn't be higher. If the vacuum's energy were just slightly stronger, galaxies would never have formed. Slightly weaker, and gravity would have crunched the cosmos into oblivion. This razor-thin balance hints that either our theories are incomplete or the universe is far stranger and far more finely tuned than we ever imagined. Until we crack this puzzle, the vacuum catastrophe remains both a humbling reminder of science's limits and a beacon guiding us toward the next revolution in physics. What if you could build a clock that ticks forever without ever winding down, a structure that defies time itself by oscillating eternally, even in its lowest energy state? This isn't a paradox, it's a time crystal, one of the most bizarre and groundbreaking discoveries in modern physics. Unlike ordinary crystals where atoms arrange themselves in repeating patterns in space, time crystals exhibit patterns that repeat in time, like a snowflake that melts and refreezes in an endless loop without any energy input. The secret lies in the quantum vacuum's hidden symmetries, where the lowest possible energy state isn't a static void but a playground of perpetual motion. The idea was first proposed by Nobel laureate Frank Wilczek in 2012, and it sounded impossible. Traditional physics says systems in equilibrium, their ground state should settle into stillness. But time crystals break this rule by exploiting a phenomenon called spontaneous symmetry breaking. Imagine a perfectly symmetrical roulette wheel. When the ball lands on red or black, the symmetry is broken. Similarly, time crystals choose a rhythmic pattern, locking into oscillations that repeat with clockwork precision, even though the underlying laws of physics don't favor any particular moment in time. Lab experiments have brought these theoretical curiosities to life. In 2017, researchers used chains of ytterbium ions or nitrogen vacancies in diamonds, nudging them with lasers to observe these perpetual ticks. The result, a structure that oscillates indefinitely, not despite being in its ground state, but because of it. What ties this to the quantum vacuum? Time crystals are essentially vacuum fluctuations writ large. Just as virtual particles borrow energy from the vacuum to flicker into existence, time crystals borrow symmetry-breaking patterns to sustain their rhythm. This makes them more than just lab oddities. They could revolutionize quantum computing. Traditional qubits lose coherence in a blink, but time crystal-based qubits might resist decoherence, acting as flawless quantum memory. Picture a hard drive that never corrupts, where information loops endlessly in a vacuum-powered dance. The implications stretch even further. If time crystals can exist, they hint that our universe's vacuum might harbor other non-equilibrium phases, states of matter we've yet to imagine. From dark matter behaving as a cosmic scale time crystal to new forms of energy storage, the possibilities are as boundless as the vacuum's secrets. Time crystals don't just challenge our understanding of matter, they whisper that the universe's quietest corners might be its most dynamic. Forget everything you think you know about particles, their masses, their sizes, even their very existence as discrete objects. What if the quantum vacuum harbors something far stranger, entities that aren't particles at all, but ripples in reality so featureless they defy all conventional scales? Meet the unparticle, a speculative, almost poetic idea from physicist Howard Georgi, proposing that the vacuum might contain stuff that doesn't play by the standard rules of particle physics. Unlike electrons or quarks, unparticles have no fixed mass, no definite size, and no clear boundaries in space or time. They're more like shadows cast by the universe's hidden geometry, leaving traces we can't explain with ordinary matter. The magic lies in scale invariance, a property where something looks the same no matter how much you zoom in or out. Fractals in nature, like coastlines or ferns, exhibit this quality, but unparticles take it to an extreme. Imagine shaking a jar of sand and watching it settle into patterns. Normal particles would behave like individual grains, but unparticles would flow like a liquid, their collective motion indifferent to whether you're observing a single speck or the entire jar. In theory, this could explain why dark matter, the invisible glue holding galaxies together, eludes detection. If dark matter isn't made of particles but of unparticled stuff, it wouldn't interact with light or matter the way we expect. It would just be omnipresent and aloof, like a cosmic fog woven into the vacuum's fabric. High-energy physicists began taking this idea seriously when they realized certain theories, like those involving extra dimensions or hidden shadow sectors of reality, naturally give rise to scale-invariant behavior. Collider experiments could, in principle, spot unparticles indirectly. If they exist, they'd leave jagged, non-integer energy signatures in particle collisions, like finding footprints that don't match any known animal. So far, no smoking gun, but the Large Hadron Collider has flagged a handful of anomalous events that resist conventional explanation. Perhaps the wildest implication is that unparticles might blur the line between matter and force. In quantum field theory, particles are excitations in fields, the electron field, the quark field. But unparticles could represent a field that doesn't quantize neatly into particles at all, behaving more like a primal, undifferentiated energy. Picture the early universe before symmetry breaking, when forces and matter were indistinguishable. Unparticles might be relics of that era, frozen in a state that predates the very concept of a particle. If proven, this would rewrite not just particle physics but cosmology. The vacuum's energy budget, dark matter's nature, even the inflationary epoch of the Big Bang, all could hinge on scale-invariant shadows lurking in the void. Until then, unparticles remain a tantalizing what-if, a reminder that the universe's deepest truths might not resemble anything we've yet imagined. Picture a river flowing effortlessly, with no rocks to disrupt its path, no friction, no turbulence, just pure, uninterrupted motion. Now imagine that same frictionless flow not in water, but in the fabric of spacetime itself. This is the radical idea of vacuum superfluidity, a proposal that on the tiniest scales, the quantum vacuum might behave like a cosmic superfluid, gliding without resistance in ways that defy our everyday experience of motion and viscosity. The concept isn't entirely out of left field. In nature, we already see hints of this behavior in places where matter is pushed to extremes. Take neutron stars, the ultra-dense corpses of supernova explosions. Here, protons and electrons are crushed together into neutrons, forming a quantum soup so dense that a teaspoonful would weigh billions of tons. Yet despite this density, the neutrons inside can flow without friction, forming a superfluid that rotates in perfect lockstep with the star's magnetic field. Similar behavior shows up in ultra-cold labs on Earth, where helium-4 chilled to near absolute zero becomes a liquid that defies gravity, climbing the walls of its container in a ceaseless, frictionless dance. If matter can achieve this state, why not spacetime itself? Some theories suggest the quantum vacuum structure might allow for pockets of superfluid-like behavior at Planck scales, where the usual rules of viscosity break down. In these regions, spacetime wouldn't drag or resist motion. It would slide effortlessly, like an ice skater gliding on a perfectly smooth rink. This could explain why particles at quantum scales seem to move in such smooth, uninterrupted paths, almost as if they're surfing on a hidden current of frictionless geometry. The implications ripple through multiple frontiers of physics. If spacetime has superfluid properties, it might offer new ways to understand dark matter, which flows through galaxies without the clumping or friction seen in ordinary matter. Some models even propose that the vacuum's superfluid tendencies could mimic the effects of modified gravity, eliminating the need for unseen dark matter altogether. And in the realm of quantum computing, engineers are already drawing inspiration from superfluid helium to design error-resistant qubits. systems where information flows as smoothly as spacetime itself might at its most fundamental level. Of course, proving vacuum superfluidity is a monumental challenge. Unlike neutron stars or lab-grown superfluids, we can't exactly scoop up spacetime and chill it in a freezer. Instead, physicists look for indirect signatures, subtle anomalies in particle interactions or gravitational waves that might betray this hidden frictionless layer beneath reality's surface. Some speculative experiments propose using ultra-precise atomic clocks to detect minute changes in the flow of time, which could vary if spacetime itself exhibits superfluid-like phases. Others suggest studying the behavior of light in extreme magnetic fields, where vacuum polarization effects might mimic superfluid dynamics. Whether or not spacetime truly flows without friction, the idea stretches our understanding of emptiness to its limits. It suggests that the quantum vacuum isn't just a passive stage but an active medium, one that might harbor properties as rich and varied as any liquid or solid we've ever known. And just as superfluid helium revealed quantum phenomena on macroscopic scales, the vacuum's hidden flows could one day unveil a universe far stranger and far more fluid than we ever imagined. In the cosmic ocean of the quantum vacuum, there's a field so pervasive that it touches every particle in existence, yet it's utterly invisible to our senses. This is the Higgs field, an ethereal medium that fills the universe like an unseen syrup, slowing certain particles down and giving them the property we call mass. But here's where things get fascinating. The Higgs field isn't just another layer of quantum noise. It operates in a way that eerily recalls Dirac's revolutionary idea of an electron sea, yet it plays by entirely different rules. Back in the 1930s, Paul Dirac imagined the vacuum as a vast, infinite sea of electrons occupying negative energy states, a dense, invisible substrate that explained antimatter and stabilized quantum theory. The Higgs field shares that same quality of being everywhere at once, a constant presence underlying reality. But while Dirac's sea was a literal ocean of particles, the Higgs is something far stranger. A quantum field that interacts with particles not by dragging on them but by resisting their motion. Imagine wading through waist-deep water. The resistance you feel isn't because the water is made of tiny obstacles, but because the medium itself imposes a kind of friction. That's how the Higgs works. When particles like quarks or electrons move through it, they don't collide with anything. Instead, they interact with the field, which pushes back just enough to endow them with inertia, the resistance to acceleration we perceive as mass. The brilliance of this mechanism is how selectively it operates. Photons, for instance, zip through the Higgs field entirely unaffected, which is why light has no mass. The W and Z bosons, carriers of the weak nuclear force, interact so strongly they become incredibly heavy. And the Higgs boson itself, it's like a ripple in this universal field, a particle that emerges when the Higgs field is excited, proof that the field isn't just a mathematical abstraction, but a dynamic physical entity. Yet unlike zero-point energy, which is a frenetic storm of virtual particles, the Higgs field is eerily calm. It doesn't fluctuate wildly or borrow energy from the vacuum. Instead, it maintains a constant, non-zero value everywhere, a feature called the Higgs vacuum expectation value. This stability is crucial. If the Higgs field were to suddenly drop to zero, mass would vanish, atoms would disintegrate, and the universe as we know it would cease to exist. The fact that it doesn't, that the Higgs field remains steadfast, is why we're here to ponder it at all. The contrast with zero-point energy couldn't be sharper. Zero-point energy is chaotic, a seething froth of particles popping in and out of existence. The Higgs field, by comparison, is more like the deep, still currents beneath that froth, a silent scaffold that shapes reality without adding to the turbulence. Together, they paint a picture of the vacuum as both a storm and a statue, wild and unpredictable at one scale, yet eerily orderly at another. What's most astonishing is how these two ideas, Dirac's sea and the Higgs field book and the history of quantum physics. Dirac's vision was a desperate fix for a mathematical crisis. The Higgs was a prediction waiting decades for confirmation. One tried to explain where particles come from, the other explains what gives them substance. And both remind us that the vacuum isn't empty. It's the universe's most active construction site, tirelessly building everything from nothing. Einstein's theory of general relativity paints spacetime as a smooth, geometric fabric, bending under the weight of stars and galaxies. Quantum mechanics, on the other hand, describes a seething, probabilistic world where particles flicker in and out of existence. These two pillars of physics seem irreconcilable except for one eerie possibility. The quantum vacuum's entanglement might be the hidden thread stitching them together. At the heart of this idea is entanglement entropy, a measure of how deeply quantum systems intertwine. Normally, we think of entanglement as a property of particles, but the vacuum itself is entangled on microscopic scales, with regions of spacetime knit together by invisible quantum links. This isn't just abstract math, it could explain spacetime's very structure. Take the ER=EPR conjecture, a bold proposal by physicists Juan Maldaisner and Leonard Susskind. They suggested that entangled particles' EPR pairs might be connected by microscopic wormholes, Einstein-Rosen bridges, or In other words, entanglement doesn't just correlate particles, it physically links them through spacetime's hidden geometry. Imagine two electrons entangled across the galaxy. According to ER=EPR, their connection isn't some ghostly signal, it's a tiny, Planck-scale tunnel woven into the vacuum's fabric. The vacuum's entanglement entropy, then, isn't just a curiosity, it's a blueprint for how spacetime stitches itself together. Here's where things get radical. If entanglement builds spacetime, then the vacuum's quantum links might give rise to gravity itself. In holographic theories, the entanglement entropy between regions of space follows equations eerily similar to those governing gravitational dynamics. It's as if gravity isn't a fundamental force but an emergent property of the vacuum's tangled web, a cosmic illusion created by the sheer density of quantum connections. This perspective flips traditional physics on its head. Instead of spacetime curving and creating gravity, the vacuum's entanglement could be the root cause, with curvature emerging as a side effect. Experimental clues are scarce but tantalizing. The entanglement entropy of black holes calculated by Stephen Hawking and Jacob Bekenstein matches predictions from quantum field theory, suggesting a deep link between information and geometry. Meanwhile, lab experiments with entangled particles in superconducting circuits hint at how quantum connections might mimic spacetime's structure. While we can't yet probe Planck-scale wormholes directly, these analog systems offer a glimpse into how the vacuum's quantum threads might weave reality's canvas. The implications are staggering. If spacetime is built from entanglement, then the vacuum isn't just empty, it's a dynamic information processing network. Black holes could be knots of hyper-entangled links, their event horizons marking boundaries where the vacuum's threads fray. The Big Bang might have been a phase transition in this quantum network, a moment when entanglement patterns crystallized into the spacetime we recognize. Even the arrow of time could emerge from the one-way growth of these connections, yet mysteries remain. Why does the vacuum's entanglement entropy follow geometric laws? Can we ever observe these Planck-scale wormholes, or are they forever beyond our reach? For now, the vacuum's quantum knots remain hidden, but each calculation, each experiment, pulls us closer to a truth that could unite relativity and quantum mechanics. Not in conflict, but in a dance choreographed by entanglement itself. The void isn't silent, it's humming with connections, and in those whispers we might finally hear the universe explain how it built itself from nothing. What if everything around you, the stars, the air, even your own thoughts, were nothing more than lines of code in an unfathomably complex simulation? It sounds like science fiction, but some physicists have begun to wonder whether the quantum vacuum's strange behavior might be the glitches in the matrix, tiny hints that reality isn't as solid as it seems. At the heart of this speculation lies the Planck scale, the smallest conceivable unit of space and time. Just as a digital image breaks down into pixels when you zoom in too far, space-time itself might be pixelated at this infinitesimal level, with the vacuum's fluctuations acting like the static between the pixels of the universe. Think of it this way: in a video game, the world looks smooth and continuous until you examine it closely. Then you notice the jagged edges, the textures that repeat, the limits of resolution. The quantum vacuum's spontaneous particle creation could be similar evidence that the universe has a built-in render distance, a point where the simulation stops pretending to be perfectly smooth. Even stranger, the holographic principle suggests all the information needed to construct our three-dimensional reality might be encoded on a two-dimensional surface at the universe's edge, like a cosmic DVD storing a 3D movie. If true, the vacuum's energy and fluctuations wouldn't be fundamental, they'd just be projections, shadows of deeper computations happening somewhere beyond our perception. Philosophers have wrestled with these ideas for centuries, from Descartes' evil demon to Nick Bostrom's modern simulation hypothesis. But the quantum vacuum adds a chilling twist. If we're living in a simulation, its programmers wouldn't need to perfectly calculate every atom in every star. Instead, they could use the vacuum's unpredictability as a shortcut, like a video game that only generates detailed graphics when a player is looking. The rest could run on probabilistic noise, saving computational power. This might explain why quantum particles don't have definite states until observed. They're loading screens, filling in the details just in time to keep the illusion seamless. Of course, not everyone buys the simulation argument. Critics point out that the Planck scale's pixelation is purely theoretical. We'll likely never build tools small enough to probe it directly. Others argue that even if the universe behaves like a simulation, that doesn't mean it is one. The vacuum's quirks could simply reflect laws of physics we don't yet understand, not evidence of some cosmic computer. And then there's the existential question. If we're in a simulation, who's running it? Are they themselves simulated, creating an infinite regression of nested realities? Yet the speculation persists because it taps into a deeper truth about physics. The more we learn, the more the universe feels like an intricate puzzle box with no final layer. Whether the vacuum's fluctuations are glitches, artifacts, or just nature's way of keeping us guessing, they remind us that reality, simulated or not, is far stranger than we ever imagined. Imagine a civilization so advanced that it doesn't just build machines, it engineers the very fabric of empty space. Vacuum engineering sounds like science fiction, but the quantum vacuum's bizarre properties could one day enable technologies straight out of a futurist's wildest dreams. Take energy extraction. The vacuum isn't truly empty, it's a seething reservoir of zero-point energy. In theory, if you could stabilize virtual particles flickering in and out of existence, you might tap into an inexhaustible power source. Some proposals involve Casimir cavities, nanoscale structures that trap virtual photons, converting their energy into usable electricity. The catch: harvesting this energy without violating thermodynamics is like trying to bottle lightning. Every scheme so far either requires more energy than it produces or runs afoul of quantum no-go theorems. Yet labs are inching closer. In 2021, researchers at the University of Manchester demonstrated a microscopic engine powered by vacuum fluctuations, hinting that controlled extraction might not be forever out of reach. Then there's the Holy Grail, warp drives. Miguel Alcubierre's famous theoretical design proposes stretching spacetime itself, creating a bubble where the ship rides a wave of compressed vacuum ahead and expanded vacuum behind. The trick: negative energy, something the quantum vacuum might provide via exotic phenomena like squeezed states or Casimir effects. While the energy requirements are currently astronomical, think converting Jupiter's mass into pure energy. Scaled-down versions could revolutionize propulsion. Recent breakthroughs in metamaterials, synthetic structures that bend light in unnatural ways, suggest we might one day mimic warp-like space-time distortions in the lab. Imagine spacecraft that don't move through space but with it, sidestepping light speed limits by rewriting the rules of the vacuum itself. But vacuum engineering isn't just about grand cosmic feats. On the microscopic scale, Casimir forces could power nanomachines with no moving parts. Picture a gearbox where plates attract or repel each other through quantum fluctuations, enabling frictionless nanorobots for medical applications. Early prototypes already exist. Researchers at Purdue University designed a Casimir-driven actuator that shifts position based on vacuum forces alone. The challenge, controlling these effects without components sticking irreversibly, a hurdle nanotechnology labs are tackling with atomic layer coatings and magnetic levitation tricks. Of course, tampering with the vacuum's fabric raises ethical dilemmas. Extracting zero-point energy on a large scale might destabilize local space-time with catastrophic consequences we can't yet model. Warp drives could generate black hole-like singularities if mishandled, and Casimir nanotech, if weaponized, might enable undetectable assassination tools. Think microscopic devices that manipulate cells using vacuum forces. The vacuum isn't just a resource, it's the foundation of reality. Engineering it demands humility alongside innovation. The future of vacuum tech lies somewhere between daring ambition and profound caution. One day, we might regard the quantum vacuum not as an empty stage, but as the ultimate workshop where the boldest engineers sculpt spacetime itself. Until then, its mysteries remind us that the universe's most potent tools often come with the sharpest edges. Out in the vast emptiness of space, there's no sound to carry, no air to vibrate, just an eerie, impenetrable silence. Yet this stillness is an illusion. Beneath the cosmic quiet, the quantum vacuum hums with an orchestra of particles flickering in and out of existence. A hidden symphony of energy that defies the very idea of emptiness. This paradox, the silence of space versus the deafening quantum noise beneath, holds the key to one of interstellar exploration's greatest challenges. How do we communicate across a vacuum that's anything but vacant? Think of space as an ocean. On the surface, it's calm and motionless, no waves, no ripples, just an endless stretch of nothingness. But dive deeper, and you'll find currents, turbulence, and invisible forces churning beneath. The quantum vacuum works the same way. To our senses, it's the perfect void, but at scales smaller than an atom. It's a storm of virtual particles, electromagnetic fluctuations, and zero-point energy. These aren't just abstract ideas, they have real-world consequences. Take radio waves, our primary tool for cosmic communication. As signals travel through space, they don't just fade with distance, they interact with the vacuum's quantum noise, scattering and distorting in ways that can garble messages across light years. It's like trying to hold a conversation in a hurricane, except the wind is made of probability waves and ghostly particles. This noise isn't just background static. Quantum fluctuations can spontaneously create particle-antiparticle pairs, which might briefly absorb or redirect electromagnetic waves. Over interstellar distances, these tiny interruptions add up, forcing engineers to design redundancy into every transmission. The Voyager probes, now drifting beyond our solar system, rely on error-correcting codes to ensure their faint whispers aren't drowned out by the vacuum's subtle interference. Even laser communication, the next frontier in deep space networking, must account for the vacuum's refractive quirks. Photons traveling through empty space don't just move in straight lines, they're subtly deflected by the same quantum froth that bends starlight around galaxies. Yet the vacuum's noise isn't just an obstacle, it's also a clue. Some physicists speculate that advanced civilizations might exploit quantum fluctuations for communication, encoding data in the vacuum's very structure. Imagine modulating zero-point energy like a cosmic radio, transmitting messages by tweaking the fabric of spacetime itself. While this remains speculative, lab experiments have already demonstrated vacuum squeezing, where quantum noise is manipulated to enhance signal clarity. If scaled up, such techniques could unlock entirely new ways to converse across the stars. The silence of space, then, is a cosmic sleight of hand. What seems like emptiness is a dynamic, ever-shifting medium, one that muffles our signals even as it whispers its own secrets. As we reach further into the void, we're learning that the greatest challenge isn't crossing the distance between stars, but deciphering a universe where nothing is ever truly silent and nothing is ever truly empty. The quantum vacuum, as we know it, a seething arena of virtual particles and fluctuating fields, is painted by quantum electrodynamics or CED with stunning precision. But what if that picture is incomplete? Beyond QED's domain, alternative theories of quantum gravity like loop quantum gravity and string theory propose radically different visions of the vacuum, each rewriting the rules of emptiness in ways that could upend our understanding of reality. Loop quantum gravity, for instance, trades the smooth, continuous spacetime of general relativity for a granular, pixelated universe. Here, the vacuum isn't a fluctuating field but a network of interwoven, spin foams, tiny, discrete loops of spacetime that vibrate and connect like a cosmic mesh. In this view, vacuum fluctuations aren't particles popping in and out of existence but twists and knots in the fabric of spacetime itself, the unsettling implication. At scales smaller than the Planck length, the vacuum might not fluctuate at all. It could freeze into a crystalline structure, eliminating the infinities that plague QED's calculations. String theory takes a stranger path. It replaces point-like particles with vibrating strings, each note in their harmonic symphony corresponding to a different particle. The vacuum, then, isn't just a stage. It's a higher dimensional landscape where strings weave through hidden dimensions, their vibrations sculpting the laws of physics. Some versions of the theory posit a landscape of vacua, each with unique properties like bubbles in a cosmic froth. Our universe would occupy just one bubble, its vacuum energy set by chance during the Big Bang. This could explain the cosmological constant problem. If countless vacua exist with varying energy densities, we simply inhabit one where life is possible. Yet for all their elegance, these theories struggle where QED shines. QED's predictions like the Lamb shift or the electron's magnetic moment match experiments to 12 decimal places. Loop quantum gravity and string theory, by contrast, are notoriously hard to test. The energy scales where their vacuum effects become obvious are trillions of times beyond our particle collider's reach. Even so, subtle clues might lurk in cosmic microwave background anomalies or gravitational wave signatures, hints that the vacuum's true nature is subtler than QED alone can capture. The tension between these frameworks isn't just academic. If loop quantum gravity is right, black holes might not evaporate via Hawking radiation but dissolve into spacetime's fundamental loops. String theory's extra dimensions could allow vacuum energy to leak into other universes, softening the vacuum catastrophe. These aren't minor tweaks, they're potential revolutions waiting for a single experimental thread to unravel the tapestry. Until then, the vacuum remains a riddle, its secrets hiding in plain sight between the lines of competing equations. What happens when you peer into the quantum vacuum, trying to pin down its fleeting particles? The very act of looking forces the void to make a choice, shifting from a haze of infinite possibilities into a single, measurable reality. This is the observer effect, the startling notion that measurement doesn't just record quantum phenomena, it creates them. At the vacuum's edge, particles exist as probability waves, ghostly drafts of what could be, until an interaction collapses the wave function, forcing a decision. But here's the catch: no one agrees on what actually triggers this collapse or even what it truly means. The Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg, treats this collapse as a fundamental boundary between the quantum and classical worlds. In this view, the vacuum's probabilities remain unresolved until a conscious observer, or at least a macroscopic measuring device, interacts with them. It's as if the universe holds its breath until someone looks, then snaps into focus. This idea unsettled even Einstein, who famously protested that the moon shouldn't exist only when we're watching it. Yet for all its paradoxes, Copenhagen remains the pragmatic choice for most experimentalists, perfectly predicting lab results even as it dodges deeper metaphysical questions. Enter the many worlds interpretation, where measurement doesn't collapse anything, it splits reality instead. Every quantum possibility plays out in a branching multiverse, with the vacuum birthing infinite alternate timelines. In one world, an electron spins up, in another, it spins down. The vacuum isn't a stage but a kaleidoscope, fracturing with every observation. While this avoids the need for conscious observers, it demands an almost extravagant cosmic budget, an ever-expanding tree of universes, each carrying the weight of its own history. Then there's objective collapse theory, which posits that wave functions collapse spontaneously, no observer required. Gravity, noise, or some as yet unknown mechanism forces the vacuum's hand, making large-scale quantum superpositions impossible. Proposals like Penrose's gravitational collapse suggest spacetime itself gets strained by quantum uncertainty, snapping into definiteness like an overstretched rubber band. If true, the vacuum's fuzziness isn't just a measurement quirk but a dynamic process woven into the fabric of reality. The implications ripple far beyond philosophy. Quantum computing relies on maintaining superpositions, states where particles are both 0 and 1 until measured. If objective collapse is real, it might set a hard limit on how large a quantum system can grow before gravity forces a choice. Meanwhile, many worlds hints that every quantum decision spawns new universes, with the vacuum serving as an endless engine of creation, and Copenhagen. It keeps us humble, reminding us that some truths might always lie just beyond the edge of observation. So does the quantum vacuum truly crystallize only when we look? Or is our gaze just one thread in a tapestry of infinite realities? The answer might depend less on the void itself than on how boldly we're willing to redefine what it means to exist. From flickering virtual particles to the cosmic hologram, from zero-point energy to the holographic universe, we've journeyed through 30 mind-bending mysteries hidden in the quantum vacuum, and one truth stands clear: the line between nothing and everything doesn't just blur, it vanishes entirely. What we once called empty space is now a frontier richer than any starfield, a realm where particles dance in and out of existence, where black holes leak secrets, and where the very fabric of reality might be stitched together by quantum entanglement. The vacuum isn't passive, it's the universe's most dynamic artisan, shaping matter, bending light, and perhaps even birthing universes. Think about it: every cubic centimeter of nothing contains more energy than all the matter we've ever observed, yet we can't touch it. The vacuum whispers to electrons, nudging their orbits. It tugs at metal plates in lab experiments. It might hold the key to dark energy, or the reason our universe exists at all. And yet, for all we've uncovered, the deeper we dig, the more questions we find. Is the vacuum the ultimate stage, or is it the director of the cosmic play? Could advanced civilizations one day harness its secrets to warp spacetime, or are we forever grasping at quantum shadows? This is why the vacuum isn't just a scientific curiosity, it's a mirror reflecting how much we don't know. Every mystery we've explored today, from the Casimir Effect to vacuum decay, from unparticles to time crystals, is a doorway to a larger truth. reality is far stranger, far more interconnected than our classical intuitions ever allowed. The quantum vacuum challenges us to rethink not just physics, but the very nature of existence. So here's the invitation: keep questioning. Pick your favorite mystery from these 30 and dive deeper. Was it the eerie silence of space that isn't silent at all? The holographic principle that suggests we're living in a cosmic projection? Or maybe the haunting idea that our universe could rewrite itself in a heartbeat through vacuum decay? Share your thoughts below, and if you're hungry for more journeys to the edge of understanding, hit subscribe. The cosmos isn't done surprising us, and neither are we. After all, the greatest discoveries often begin by asking, what if? And the quantum vacuum is the ultimate playground for that question.